Hello. Oh. Okay. Hello, I'm Sirui from OpenAI, and today I will introduce HieraSynth, which is a parallel and complete superoptimizer framework. So this is not an OpenAI work, and it's developed during my PhD at UW with my advisor, Bodík from Google DeepMind. So optimizing vector code by hand for performance can be extremely challenging and time-consuming. So consider a practical example from Google's Highway library. So suppose we want to compare 128-bit numbers packed in vectors. So ideally, we would use native 128-bit instructions. But since our hardware only supports 64-bit lanes, we must emulate these instructions. So currently, the expert written implementation uses 14 RISC-V instructions. So the key question is it the best, or can we further optimize it? So we can definitely do this manually, but exploring such optimizations takes too much precious expert time. So it is better to automate this process. So using our tool, HieraSynth, we systematically search the entire program space under the Sci5x280 cost model, and we discovered a program that is 5.7x faster. So this allows the experts to confidently adopt the optimized code without further manual tuning. So let's briefly explore how the superoptimizers work. So given a reference program, a superoptimizer searches a large program space exhaustively to find the optimal solution that matches a specification. So the primary challenge here is the sheer size of the program space. So it typically grows exponentially with the program length k and also the size of the ISA n. So this exponential growth makes complete search increasingly impractical as the program's growth or like the instruction sets becomes larger. So a common solution for scaling superoptimizers is to use a peephole-style sliding window. So imagine a superoptimizer that optimizes small segments, say sequences of 2 instructions. So we can repeatedly apply this peephole approach, and then we can optimize this large program incrementally. But however, this approach lacks a global view, and it cannot guarantee its optimality. So this can mean some potential improvements that requires a holistic analysis of the semantics, and we might not be able to be confident enough that we don't need to do further improvement over it. So we need to address this limitation by scaling the superoptimization efficiently while preserving the completeness. So with this background, we analyzed the capability of the existing tools, and we observed a surprisingly consistent regression line. And this reveals a strong inherent scalability limitation across the existing superoptimizers. But if we want to search for the realistic vector kernels and ensure the optimality as much as we can to gain the confidence, we will need to handle program spaces that is far larger than what the existing tools can manage. And our goal is to break the existing frontier and push it to these challenging problems. So our strategy is simple, but very powerful. So we start from a strong base synthesizer suited for long programs, and we adapt it to handle significantly larger instruction sets by hierarchically decomposing the instruction set selection. So we choose the component-based synthesis as our base synthesizer because it is good at synthesizing long programs. So this approach models the program space as a multi-set of components, and it synthesizes by reordering and wiring these components into a directed acyclic graph. So this approach is highly effective if we know the right components or instruction by our human insight, but it will struggle with large ISAs due to some excessive redundancy in the program space. So the reason is that it is effectively creating a program space where the k exceeds n because the instructions must be duplicated many times to fully cover the desired program space. And this violates our large ISA assumption. So our solution introduces another hierarchy by embedding the choices within these components. So this synthesizer can now select the optimal instruction within each component in addition to reordering and wiring. So this could greatly reduce the redundancy, and this could help us achieve about 10 times speed up. But this is actually not enough, and the program space can still be overwhelming with very large ISAs. So to solve this, we partition the large program space into smaller, more manageable subspaces, and we can then search these subspaces independently and in parallel. And also, since our partition do not lose any program, our approach is still able to search completely and preserve the optimality. And then the next question will become how to choose the right decomposition granularity. So if we have a coarse decomposition, this could leave subspaces that are too large to solve practically. Or if we use overly fine decomposition, this could give us too many subspaces, and the solving overhead can be intolerable. So finding the right level of decomposition is essential. So to achieve the optimal granularity, we use an adaptive hierarchical partitioning scheme. So we dynamically decompose only the harder ones, and this efficiently balances the complexity across the subspaces. So this hierarchical decomposition is enabled naturally by our program space representation. So for example, here, given 3 identical components in the program space, we can split them into 2 subsets and enumerate how many components are chosen from them. And we can do this further until the program space are easy enough. So here, each step here gives m+1 subspaces for the component repeated m times instead of an exponential growth for the single step. So we can gradually split our components into smaller subsets in an adaptive manner. And then we can solve these subspaces in parallel with 3 possible outcomes. So if a subspace is unrealizable, we will simply prune its entire subtree. Or if a subspace is too challenging, we will further partition it adaptively to find the right program space size. Or if we successfully synthesize a program, we can refine it to minimize the cost and eventually prove optimality within that program space. So when every leaf node is proven optimal or unrealizable, we will get a globally optimal solution. And also to make this search practical, we also need some tricks. So we speed up the unrealizability proofs via a 2-track synthesis approach with some lighter weight detection. And we also balanced the exploration and the exploitation with biased search strategies informed by the successful searches. And please have a look at our paper for the discussion on these important tricks. Then for the evaluation, we evaluate HieraSynth to understand a few questions. So we have already covered the speed up with our new program space representation. And we would love to understand first, have we achieved our initial goal of pushing from the frontier and synthesize realistic vector kernels? And second, how performant are the synthesized kernels? And third, how good can we take advantage of parallelism? So we evaluate these questions on 1 set of scalar benchmarks and 2 sets of realistic vector programs taken from Highway and VQ sort. And here is our result. So we can see that with HieraSynth, we can greatly push past the previous KN frontier established by the prior tools. And we can scale up both the maximum synthesizable program size and also the ISA size. And we can synthesize up to 5x larger programs if we fix the ISA, or over 10 times larger instruction sets with the same length. And also an important thing here is that for many synthesized solutions, we can even prove that they are optimal with our cost model. So this wasn't usually available with the existing tools. And here we show the time spent for synthesizing the vector programs. So we have sorted them with the estimated size of the program spaces, and we can see the correlation. And here for the simpler programs, we can explore the whole program space in very short time, just a few seconds. Then for the synthesized programs, HieraSynth found significant speedups, and more than half among the benchmark set achieves at least 2x speedup. So here we report the numbers with LMO set to 1. LMO is a configuration for RISC-V instruction set. And for some benchmarks, the synthesized kernel could have larger speedups with higher LMOs. And also we have contributed many of them back to the upstream. And also, HieraSynth scales effectively with more computational resources. And here we show the synthesis speedup relative to the single core performance. So especially for the complex kernels, using up to 72 cores greatly reduces the time required to synthesize the best known programs or prove that they are optimal. And we can achieve near linear speedup on some of them. So this shows a great parallel efficiency, and we can anticipate that for some highest value kernels, we may throw thousands of cores and further pushes the scalability. And to conclude, we present HieraSynth, a framework for building super optimizers. And we would love to emphasize that the approach itself is general and do not tie to our specific program space representation. And the same decomposition idea could be used to scale other program synthesizers. And thank you, and I will take any questions now.
Thanks for the interesting talk. So my previous understanding of component-based synthesis is still based on SMT solving, right?
Yeah, we are using SMT solvers.
You know the solver itself can support multi-thread solving, right? So what's the reason for you to do the splitting by yourself, or why not use their multi-thread? Is it useful, or just you didn't try it?
Yeah, because we observed that using this more principled approach for partitioning the program space instead of partitioning on top of the SMT solvers could give us more scalability.
Thank you.
Yeah.
Very nice. So you are focused very much on RISC-V, I understand, right? You are focused very much on RISC-V.
Yes, we are working on the RISC-V instruction set.
How much work is it to, where is the hard work of porting it to something else?
Oh yeah, so we have built the HieraSynth as a library. So basically that library is ISA agnostic. And then on top of that library, we built our synthesizer for RISC-V. So basically, to pour this to another ISA, what you need to do is to implement the semantics of that ISA as a symbolic evaluator using the HieraSynth, and then you will get a synthesizer. Yeah.
Very nice talk. I guess my question is, it seems your approach is can be generally applied to any program, but your evaluation focus on vector program. So is there any specific insight that you think why it does so good in vector programs?
Yeah, I think the reason why we choose a vector program as the target is because it is posing the unique challenge of a very large instruction set. Because normally, if you are working on the scalars, you probably only work with maybe 10 or 100 instructions. But using vector instruction set, if you have ever read the RISC-V or the RISC-V intrinsics guide, it is a file with more than 4,000 pages. So it is giving you a really large search space. And our approach is focusing on scaling with large ISAs. So that's why we choose vectors as our target. Yeah.
I see. Thank you.